A laboratory in Hefei fires a single pulse of light through a fixed maze of mirrors and beam splitters, and on the far side a pattern of photon clicks falls out that no ordinary computer on Earth can reproduce in any useful stretch of time. A few thousand kilometers west, a different kind of processor sits inside a chamber cooled colder than the space between stars, holding fragile artificial atoms steady long enough to start correcting their own errors. Two roadmaps to a working quantum computer are running at the same time, on opposite sides of an export restriction that was supposed to slow one of them down. The bet on light versus the bet on cold metal just repriced, and here is where the odds actually sit. When export controls cut China off from the supply chains feeding a cryogenic, chip fab-dependent superconducting program, the country's quantum effort did not stall. It pivoted to photons instead, a path that needs no dilution refrigerator and no foundry access most Western labs assumed was the only route in. That substitution is the contested fact under everything that follows, because nobody who wrote those restrictions priced in a workaround built from mirrors and beam splitters catching up this fast. The two wagers on the table are straightforward to state. Bet 1 is China's photonic path, routing single photons through a fixed optical network at room temperature and betting on raw sampling speed to prove a quantum advantage now, with general-purpose computing to be solved later. Bet 2 is the Western superconducting path run by Google and IBM, building artificial atoms out of superconducting circuits near absolute zero and betting that a smaller number of reliable logical qubits beats a large pile of fragile physical ones. Price each claim against its sharpest rebuttal, escalating toward the harder evidence. Bet 1's strongest case is manufacturability. A photonic chip runs at room temperature, skips the cryostat entirely, and can in principle be built on optics and photonics fabrication lines that already exist far outside the narrow circle of foundries that make superconducting qubits. The rebuttal is that a fixed sampling network is not a programmable computer at all. It is wired for one task, and reconfiguring it for a different problem looks closer to rebuilding the optical table than updating software. China's Zhejiang line of photonic processors has, by the research group's own published account, detected roughly 76 photons in its original demonstration, producing sampling patterns the team estimates would take a classical supercomputer an impractical stretch of time to match. Both that photon count and the classical time estimate come from the group itself and its follow-up papers, and neither has been independently reproduced on equivalent hardware by an outside lab, and the classical comparison has already shifted as competing algorithms improved. The line moves toward bet 1 on sheer demonstration speed and toward bet 2 on practical relevance, so the net move sits close to flat, with the slightest lean toward bet 1 for having a working demonstrator running sooner than its rival. Here is the flat concession this pricing owes the audience. On the metric of general-purpose usefulness, photonic sampling machines plainly lose to programmable, superconducting processors. A Zhejiang-class chip cannot be pointed at an arbitrary algorithm, it does one fixed task, while a superconducting processor, however noisy, can in principle be reprogrammed for different problems. That gap is real, and nothing in the rest of this pricing erases it. Bet 2's strongest case has grown to 2 data points instead of 1. Google's Willow chip reportedly demonstrated that adding more physical qubits to a logical qubit can shrink the error rate rather than compound it. The long-sought threshold the entire superconducting roadmap has been built around, and IBM has separately published a roadmap betting on linking several smaller superconducting processors together into one modular system instead of growing a single chip indefinitely. The rebuttal cuts 2 ways. On scale, the chip's own published qubit count in the low hundreds still sits far short of what most independent error correction estimates say a single fully fault-tolerant logical qubit needs for real work. On independence, 2 superconducting teams converging on error correction as the priority is not outside confirmation. It is one physics platform hedging its bets internally rather than 2 rival platforms agreeing. Reports describe Willow as an array on the order of 105 qubits, by the company's own count, with below-threshold scaling observed across several rounds of increasing array size, while IBM has described in its own statements a path toward fault-tolerant operation later this decade. No outside lab has yet confirmed either company's intermediate milestones, and most independent estimates still put a genuinely fault-tolerant machine years away. Even so, 2 well-funded labs landing on the same bottleneck from different engineering choices is meaningful signal, and the odds move firmly toward bet 2 here, the sharpest swing in this whole pricing. Bet 1's counter is that photonic qubits resist decoherence in a way superconducting circuits cannot, because a photon traveling through glass or open air is not constantly colliding with a noisy thermal environment the way a circuit chilled near absolute zero still is. The rebuttal is that photon loss is decoherence wearing a different coat. Detectors miss photons, fibers absorb them, and a missing photon does not produce a correctable error. It produces a result that simply cannot be used. Photon loss remains a primary bottleneck cited across the photonic quantum computing literature, and most groups working in this space, including teams adjacent to the Zhejiang line, treat loss tolerance as the open problem still standing between today's sampling demonstrations and a fault-tolerant photonic machine. That moves the line toward the skeptical read of bet 1 because the room temperature advantage is real, but it trades one hard physics problem for another rather than escaping the category entirely. The heaviest weighing here concerns reproducibility itself. Independent researchers have publicly questioned whether classical algorithms, refined since Zhejiang's original claims, can now simulate its sampling output faster than the photonic hardware produces it, which would quietly erode the advantage claim. The Chinese team's response and follow-up preprints has been to push photon counts and circuit depth further, arguing that the classical catch-up only proves the comparison is a moving target rather than a settled defeat. This back and forth is documented across multiple preprints on both sides. None of the rebuttal papers claiming to match the photonic output have, as of the most recent reporting, been confirmed running on hardware at comparable scale and cost, and the dispute remains unresolved in peer review. This is the strongest evidence in the whole script, and it moves the line toward the skeptical bet on the headline advantage claim specifically, even while the underlying hardware program keeps advancing. Strip away the press materials on both sides, and the decisive fact is this. Bet 2 has a credible, scrutinized path from today's noisy qubits to tomorrow's error-corrected ones, backed by two separately funded teams converging on the same physics from different directions, while Bet 1 has a faster, cheaper demonstration with no comparably credible published path yet toward a general-purpose machine. The below-threshold scaling result out of the superconducting camp is the decisive evidence because error correction, not raw sampling speed, is the bottleneck every serious roadmap in this field treats as the actual finish line. And it is the one result here reached independently by two labs using different engineering choices rather than one team marking its own progress. Think of a superposition the way you would think of a coin spinning in the air rather than resting heads or tails on a table. It genuinely holds both outcomes at once until the spin stops. And a quantum processor is a machine built to do useful work during that spin. Before noise, the quantum equivalent of gravity pulling the coin down, forces a single answer out. That is what both camps are racing to exploit before the spin collapses, and it is why every gain in coherence time on either platform is worth more than it sounds. Before that price holds, three things could still unwind it. Willow's result is the company's own published claim, and like Zhejiang's advantage claim before it, independent reproduction by an outside lab on separate hardware is still pending. Every qubit count cited anywhere in this pricing on either side is a physical qubit count, not a logical one. And the leap from physical to logical qubits is exactly where quantum roadmaps have historically slipped their timelines. And both platforms remain bounded by their own version of the same problem: superconducting circuits by thermal and electromagnetic noise, photonic networks by detection and transmission loss, with neither error budget anywhere near where a commercially useful machine would need it to sit. Put together, both bets are still pricing potential rather than delivered product, which means the gap between them is narrower than either side's press materials suggest, and wider than either camp's most loyal supporters would like to admit. A handful of upcoming results could move this line hard. If an independent lab outside the original Zhejiang group reproduces a comparable photonic sampling advantage on its own separately built hardware, that confirmation would push the line sharply toward Bet 1's broader credibility, settling a question that has hung over the photonic program since its first headline. If a single logical qubit built from a Willow-class array or an IBM modular system runs an actual algorithm with a useful output, confirmed by researchers outside the originating lab, that result would push the line decisively toward Bet 2 and would functionally end this phase of the rivalry because it directly answers the rebuttal raised twice already in this pricing. If a second, larger Chinese photonic processor moves from a fixed sampling-only design towards something reconfigurable, able to be pointed at more than one kind of problem, that step would answer the clean loss concession on general-purpose usefulness more directly than any new sampling speed record could, and it would move the line toward Bet 1 harder than anything photonics has produced so far. And if a widely cited classical algorithm matches or beats a photonic sampler's output at comparable cost and time, published and independently confirmed rather than merely claimed in a preprint, that single result would hit bet 1 hardest of all, because it would not just question one demonstration, it would question whether sampling speed was ever the right proxy for quantum advantage in the first place. Priced honestly, the odds favor bet 2's error correction first path as the more likely route to a genuinely useful quantum computer, by a margin that is real but not overwhelming, closer to a modest favorite than a runaway leader, because bet 1 keeps closing distance faster than either side's own timelines predicted. A single confirmed reproduction, or one reconfigurable photonic chip, could move this line again within a year. So treat this as a live price rather than a settled verdict, since the evidence underneath both bets is younger than the rivalry itself. The restriction meant to keep China off the superconducting board did not remove the country from the table, it just handed it a different set of chips to play, and those chips now sit close enough to the pot that nobody here is folding. If you had real money on the machine that reaches useful quantum computing first, are you backing the photons running at room temperature or the circuits running near absolute zero? And why? If you want the next move in this race priced the moment it lands, subscribe.